For decades, advancing the practical use of ceramic matrix composites, also known as CMCs, has enticed, yet frustrated, the aerospace industry. Composites are separate materials that are then engineered together. Think of concrete, a primitive example of an early composite. But CMCs, they're anything but primitive or simple.
If you were to cut open a part, a ceramic matrix composite part, you would see in there, at great magnification, very, very thin silicon carbide fibers embedded in a matrix of silicon carbide. Those fibers are thinner than a human hair, by about a factor of 5. Around that fiber is a very highly proprietary coating, and that's really the key to why this material can be applied in this kind of a context. It's tough, like a metal, not brittle, like a ceramic.
The end result is an ultra-lightweight and super heat-resistant material, the perfect 1-2 punch for a multitude of industrial applications. But CMCs have proven difficult to manufacture in large quantities. Until recently, their use had been limited to large structures such as missile housings and the exhaust systems of fighter jets. But after decades of development and testing, scientists at GE's research centers across the United States have cracked the production code and are ready to integrate thousands of CMC parts into the hottest sections of jet engines. GE first developed CMCs at its Global Research Center in New York as a differentiating technology in large ground-based gas turbines for power generation. At the turn of the century, GE ran CMCs into several large gas turbines to efficiently supply electricity to homes. By 2006, those same GE scientists began applying their learnings to jet engines being developed by the company's GE Aviation business. And in 2009, GE Aviation ran its first ever CMCs in the hot section of the F-136 military engine. The components were structural CMC shrouds which direct air in the high-pressure turbine, the hottest section of an engine. The successful test emboldened GE to even more aggressively pursue CMCs for installation on its next-generation jet engines. The first production engine to integrate the new material is none other than the best-selling CFM LEAP engine. In the military world, the Air Force and GE's adaptive cycle engine features the most expansive use of CMCs throughout the engine core, setting the record for the highest hot section temperatures in aviation history. In 2014, the adaptive engine accomplished yet another industry first, rotating CMC parts located in the highest stress environment of the low-pressure turbine. But aside from their durability under unprecedented temperatures, why else would this new material be such a game changer? For one, CMCs are 1/3 the density of the metal alloys they replace. Subtracting 2/3 the weight off these components requires GE engineers to design even lighter structures supporting those featherweight CMCs. Simply put, the lighter the engine, the better the aircraft's fuel burn. But nothing beats the fuel efficiency combination of less weight under hotter operating temperatures.
Because they're made of silicon carbide, they can go to very, very high temperature. 2,400 degrees, 500 degrees hotter than the best super alloys that we can produce today. And that allows us to run more efficient engines.
Because the material can withstand unprecedented temperatures, CMCs require less cooling air rushed into its location in the hot section, where that cooling air was traditionally needed to maintain the durability of the component. Now, the newly available cooling air can be diverted back into the engine's natural flow path to improve fuel efficiency at higher thrust. As more hot section components are made of CMCs, you could see a 25% increase in thrust and a 10% improvement in fuel consumption by as early as 2020. And the movement to populate GE engines with even more CMC components has only just begun. In 2015, GE tested a GEnx engine with CMCs in the combustor and high-pressure turbine sections to mature the technology for the new GEnx engine, which will power the new Boeing 777X beginning in 2020. Clearly, the horse is out of the barn.
When we go into the hot section of the engine, where the pressure and temperature set the efficiency of the overall engine, and we replace the combustors, turbine shrouds, turbine nozzles, turbine blades, we're going to compression ratios of 60. We've run out of headroom in metals. We can't make these engines out of those kinds of materials in the hot section of the engine, so we've moved to a new class of materials called ceramic matrix composites, or CMCs.
But how will GE address the manufacturing challenge to deliver what's projected as a 10-fold increase in CMC demand through the end of this decade? Well, it all begins with the CMC fiber, the basic building block for creating the CMC material. In 2012, Nippon Carbon of Japan formed a joint venture with GE and SNECMA called NGS Advanced Fibers to produce the fibers for CMC components in the CFM LEAP engine, as well as GE military applications. NGS is doubling the size of its factory in Japan and increasing its production capability by 10 times today's rate. At the same time, GE is building its own CMC production capability in the United States. In 2015, GE announced plans to build not one, but 2 CMC facilities in Huntsville, Alabama. The first plant is co-funded by the U.S. Air Force Research Lab, and it will sell fibers to GE businesses, the Department of Defense, and other customers. The second facility, financed solely by GE, will apply proprietary coatings to those ceramic fibers to produce CMC tape, which will then be shipped to GE's new CMC manufacturing plant in Asheville, North Carolina, which opened in 2014 to produce CMC shrouds for the LEAP engine. In Ohio, GE Aviation established a CMC laboratory in its historic Building 700, which was built back in 1940 by Wright Aeronautical to build piston engines for the Allied forces. It's here where GE scientists are advancing the CMC technology while learning how to manufacture those CMCs at low volumes. Then, those learnings are transferred to GE's Lean Lab in Delaware, where the team is charged with creating the formula to mass produce the components in North Carolina, the first plant in America dedicated to CMC mass production. Even after 20 years of rapid advancement, the CMC revolution, fostered by GE, is still in its infancy. But the millions of hours and billions of dollars invested in this radical new material are finally paying off as GE propels the fuel efficiency and performance of its jet engines to new heights.